Okay, so let us start where we had left off yesterday. So we were talking about magnetostatic fields, and I'm going to talk about, in the context of magnetostatic fields, we're going to talk about magnetization. So magnetization is a process which is analogous to polarization. When dielectrics are placed in electric fields, they get polarized. When you have magnetic materials in a magnetic field, you can have magnetization. Essentially, if you have a current loop, now this current loop need not be an actual current loop, but maybe the path of a charge. So the closed path of a charge will behave like a current loop, and this current loop behaves like a dipole. So the current loop behaves like a dipole. So essentially, you have a force in this direction and another force in this direction, equal and opposite forces. You can work this out. If you work out the force on this conductor and you work out the force on this conductor, and these two forces cancel each other out when they're placed in a magnetic field, which is in the direction of B shown here. So what you will have is this entire current loop will experience a torque. It will behave like a dipole, and so the magnetic moment is defined as, remember, these are bound currents. So if this is not a real current loop, but basically the path of an electrical motion within an atom, so therefore I call it IB to differentiate it from free current I. So the magnetization magnetic pole dipole is equal to IB into S, which is the surface of the current, and it is in the direction of AN. So, for example, if these are your individual magnetic dipoles, the direction of the dipole is in this direction, and you can find this as I into L into W, which is the area of the loop into in the N direction. So the total magnetization, just like polarization, would be the sum total of all the magnetic moments in a volume delta V. So summation mk divided by delta V in the limit delta V tending to 0. So sum together all the magnetic dipoles, so one dipole moment due to one current, one LW area, take a area, sum total of all the magnetic dipoles in this region, and summation of mk divided by delta V in the limit delta V tending to 0 is the magnetization as a point function. So again, you see here you have an analogy to polarization in dielectrics. Now, if M is not 0 everywhere, then it is a material which has been magnetized. And what is the relation between the magnetization and the currents due to which magnetization occurs? We assume that magnetization occurs due to the current, the bound currents. The bound currents are because of the motion of the electrons. So curl of M is equal to JB. Curl of H is equal to J, which is the free current, and curl of M is the bound current. So if this is the case, then if you want to find curl of B at any point, you know that that is equal to mu naught into J, where J is mu naught is the permeability of free space multiplied by J. Now J is includes two types of currents. One is the free current, which is the external current, which behaves like a source, and the bound current, which is due to motion of particles within the material because it has been placed in a magnetic field. Now, JF is equal to curl of H and JB is equal to curl of M. So, since curl of B is equal to mu naught isotropic curl of H plus curl of M, it is curl over the same curl of the quantities in the same region in space. So therefore, B can be written as mu naught H plus M. B B is equal to mu naught H, so I can take out H, and M, so I can write this as mu, so this can be written as mu into mu naught H. What is mu then? Mu is mu naught into 1 plus xi m being the magnetic susceptibility of the material, and this can be written as mu naught mu r. So you see the identical, you see the analogy between permittivity and permeability. When you have no magnetizable material, you just have mu naught H, where mu naught is the permeability of free space. But when you have magnetization, there is an extra component, and the relative permeability or the permeability of the medium changes by a quantity mu r being the relative permeability of the medium, and the relative permeability is equal to 1 plus xi m, where xi m is the magnetic susceptibility. Right? This is something that we know. And therefore, now what I can do is, when I write curl of B is equal to mu naught J, I can rewrite this as curl of 1 by mu naught curl of A, B is curl of A, minus M. B is curl of A and minus M is equal to JF. So taking out the magnetization component, this is the component which is due only to the free current or the external current. So now I have a modified expression for curl of B, or in terms of curl of A, curl of 1 by mu naught curl of A minus M is equal to JF, right? Again, I should mention, if you are going to consider M as a point function, then you do not need to consider mu r. If M is equal everywhere, then the magnetization of the material is lumped in a lump parameter, which is mu r. So if you consider mu r, you do not have to consider M. If you consider mu naught, then you have to consider M. You do not need to consider both. So again, just like polarization. Now, apart from the magnetization, so we will have to take into account magnetization just as we have to take into account polarization, either through epsilon or R or with N. Apart from that, we have a special class of materials which we deal with when we talk about magnetic fields, and that is a ferromagnetic material. A ferromagnetic material is strongly magnetized by a magnetic field. That is not the problem. Problem is the the hysteresis loop, which you're all familiar with, that even once you magnetize a ferromagnetic material, even when you remove the magnetic field, some amount of magnetization will remain. The residual magnetization will be there, and to get rid of the residual magnetization, you will have to apply a field in the opposite direction, which is the coercive field. Essentially, what this means is that when you're magnetizing the material, this is the path that is followed, and when you're demagnetizing, this is the path that is followed, and this area under the curve is the loss due to the magnetization, due to the previous magnetization, the historical magnetization of the material. So how do I take that into account? So what essentially happens is the manufacturer will give you the BH curve for a particular material, because you will never have a virgin material that you're using. Let's say you're using a transformer and you have used a ferromagnetic material, and that ferromagnetic material has a BH curve which you have to obtain from the manufacturer. Now we have to take into account this BR. Even when H is 0, you will still have BR, and we need to take that into account. So if I want to take that into account in my finite element formulation, what option do I have? So that means, essentially, if you're looking at this, any point on this curve, B is no longer simply mu H, but there will be an additional quantity, B naught. Let B naught be the residual magnetism, or let B naught be constant everywhere. We know that there is actually a varying amount of extra B that is added, which depends upon H. So This value is not the same as this value, but as a first approximation, we will take an average value to be added to B naught everywhere. And what is this B naught that we are adding? The B naught that we are adding is mu into HC. What is HC? HC is the coercive field intensity coercive field intensity. It is the value, it is the magnitude of the negative field that has to be applied to bring the magnetism in the material to zero. So what we do is we make the first assumption is made here, and that is instead of considering this B naught to be a function of H, what we do is we add a constant quantity B naught to mu H to get the B at any H. In which case I can write equal to 1 minus mu B minus B naughts. Now we know this is a permanent magnetic material, so there is no field, no current involved. Therefore, curl of H is equal to 0. So if I put this expression in this equation, so I have curl of 1 by U by curl of A minus curl of 1 by mu B naught is equal to 0. Okay? Remember, this is mu. Now, how do I discretize this? So I'm going to do some kind of manipulation. What I will do is, I will take this quantity B naught and I will break it up into an X and Y components. Remember, we are dealing with fields which are only in the XY plane because we have taken a current in the JZ direction. If JZ is equal to 0, we are still concerned with a two-dimensional field just for the sake of convenience. As I said, I'm only going to use two-dimensional fields. If you have three-dimensional fields, you just break it up into two-dimensional field and do whatever I'm doing. Repeat that for every dimension. So if I am only concerned with the X and Y fields, so B naught has two components, B naught Xi and B naught Yj. Now I define a second quantity, a second vector quantity, B naught E. And B naught E has as its X component B naught Y by mu, and as its Y component B naught X by mu. So this is a manipulation that I'm doing. So therefore, my B naught E is B naught Y by mu I minus B naught X by mu J. Now, if you look at this, del X of B naught Y mu minus del Y of B naught X by mu is divergence of B naught E. I'm going to use this expression right away, so it will become clear to you why I'm doing this. Now, what do I have to do? I have an equation, and I need to find a way. In order to go from here to the finite element discretized equation, the first thing I need to do is take the weighted residual. So to take the weighted residual, this is what I do. Instead of taking what I had taken, what I had a curl of B, etc., I take residual of this expression. So weighted residual of whatever your W is, if you're using isoparametric elements, if you're using serendipity elements, you know what the shape functions are, the weighted functions. You choose your shape functions accordingly. I'm not going to talk about that. So divergence of B naught becomes divergence, Now this is scalar quantity, this is a vector quantity. So this becomes within the integration, this expression can be written as divergence of W B naught E minus B naught E dot grad W. We have faced this identity before. So these are the two quantities. Now what do? I take this quantity . This is a volume integral of a divergence of a vector. So I can write it as a contour integral. So this becomes, by Stokes' theorem or Green's theorem, contour integral of W B naught dot dl. And this remains as it is. So W is S, whatever S you use. So this is what you have. Now, as before, we will ignore the contour integral because we have seen that whenever we have a contour integral, that is contributing to the force vector and not to the stiffness matrix, and that will be which takes into account the boundary conditions. So we are not going to deal with this. We are only concentrating on the stiffness matrix. This, of course, you know how to deal with. You will deal with it and you will put it to the force vector right hand side. So what happens to the second term? The second term is integration of B naught E grad S d omega, which can be written as integral of divergence S transpose B naught E d omega. We have a dot product. So for matrices, this is what you have. If you're working with PQR, which I had given you for any elements in terms of the coordinate axis, this is how you put it in the equation. This is what you get. Now, as you can see, this term also is a quantity which does not have phi, which does not have A. And therefore, it is a term which you can evaluate if you know B naught X, B naught Y, and the coordinates. So therefore, this term also goes to the right-hand side and is added to the source term. So that makes sense. So what are we saying essentially, or what are we finding out through this discretization process is that if you have a residual magnetism, that residual magnetism behaves like an additional source term in your equation, and like all source terms, it adds to the force vector on the right hand side of your equation. It does not add to the stiffness matrix. Is this clear to everybody? Sachin, Sandeep, your friends are absent.
Ma'am, but why this B naught E is used here? Why not it can be B?
What come again?
Ma'am, why B naught E is used in the weighted residual effect?
What is not used?
Why B naught E this is used in weighted method of weighted residual?
Oh, why am I using B naught E? I'll come to that. The reason is that if I define B naught E, I can get this nice term which gives me, which lends itself to this kind of manipulation. If you work with B naught, you will not be able to use these manipulations. And there is a reason I'm using this manipulation. It's for the sake of algebraic manipulation. And how I account for that, I'll come to in the next slides. Why I'm not, since I've not worked with B naught and I've worked with B naught E, how do I take that and how do I make that okay? That I will come to the next slide. But as far as here, you can see that if you, instead of taking B naught, if you work with B naught E and you do this, this is what you get. You get a term which ends up in the right-hand side of the vector. Then let us see what happens.
Ma'am, Q and R, they are function of X and Y.
Yeah. That's the PQR I had defined in one of the very early lectures. Okay, now to answer your question. So what I have done is I have taken the weighted residual of divergence of B naught. What was I supposed to take? Which term was I supposed to have evaluated to account for the residual magnetism? This term, right? Curl of B naught. Forget about 1 by mu, that's a scalar quantity. So curl of B naught is what I should have evaluated. And this is a two-dimensional field. So for a two-dimensional field, curl of B is equal to this quantity. 1 by mu is already there. So 1 by mu curl of B is this left-hand side. And what am I doing? I am evaluating this, and then I am defining a second term B naught E such that this curl of B can be written as curl of B naught E. Okay. 1 by mu curl of B is equal to divergence of B naught E. And then I am evaluating this term instead of evaluating this term. So when I am taking the weighted residual of this quantity, I'm actually taking the weighted residual of agreed?
And the magnitude are same, but here
You have
it
to
is a
speak
vector.
louder. This AC is very loud.
Ma'am, it is a vector quantity, left hand side, and the right hand side is the scalar quantity. So only we are considering the magnitude here.
No, it's not. There is no scalar vector. It's all a vector. B is a vector. B naught is a vector.
Right hand side, ma'am, it is a dot product. So we'll get a scalar quantity.
This one.
No, ma'am. Del dot. You told del dot B naught E is equal to 1 upon mu del cross B naught. So del dot B naught E.
This one.
Yes.
No. Why should it be? It is B naught X B. See, B naught is B naught Xi plus B naught Yj. And when I take curl of B naught, I get, oh, acha, yes, this is a scalar quantity. And this scalar quantity yeah, curl of B, a curl of two-dimensional B. It's only magnitude that we are concerned with. Yeah, because it's a two-dimensional field, just as in the previous cases when we have currents, we have AX, JX. Similarly, here also curl of B is in a given direction. It is normal to the B field. Okay. So this we have done. So this is what you need to do, a repeat of whatever we had done. Summation. So phi I here we are using phi I. This would be either be P if it is a permanent magnet, or it will be A if the magnetic vector potential. But even if you're working with a magnetic vector potential, we are just evaluating the magnitude of the AX, AY, or AZ. So we proceed in the same manner. So I am not going to do this. You already know how to deal with curl of A. This we have discussed in the previous class. For a ferromagnetic material, you will have an extra term, curl of B naught, and you now know how to deal with that, and that will add to the source term. And the remaining term is as before we have shown. I have shown you that curl of A gives you. This is the quantity that you get, and this is the quantity that you need to evaluate. Discretize, which you already know. You already know how to discretize this part of the equation. And the extra part is due to the B naught, and I have told you that if you discretize that, it will add to the source term, so you know how to take care of that as well. Now, I think what you need to do is you need to take some time, a bit before, after this class and after the lab, you need to I will set you an assignment. I'll put up the formulation. You need to, because I don't think I'm going to leave it without, I could have said that you do it and don't have to submit, but I have a feeling that this class is absolutely not doing anything. And so if I give you an assignment that you do not have to submit, you're not going to do it because none of you were able to write the program in the exam. So what you have to do in this course, in this thing will be, in this assignment will be that you will write you will modify your existing program for electrostatics to account for magnetostatics for a magnetic material. So this is what you will do. And since, to round off, since we have been talking about scalar and vector potentials, and we have shown an analogy between the electrostatic fields and the magnetostatic fields. Now, in the electrostatic field, we have phi as a scalar potential. Here, we also have the magnetic scalar magnetic potential Vm, which holds when you have J not equal to 0. Sorry. Now, ordinarily for magnetic fields, you have the magnetic vector potential. Now, for the sake of analogy, we can also think of a electric vector potential T, just like A. This T is curl of T is equal to J. So, because in a conducting material, you can relate, so if you can express curl of T is equal to J, then T is a electric vector potential. So what are the equations that you have in this situation? Curl of T is equal to J, curl of E equal to 0, and E is equal to J by sigma. So you have a current in the electrostatic field, and this is how it adds up. If you take these three equations, what you get is curl of 1 by sigma curl of T is equal to 0. And this is exactly similar to the magnetostatic equation. So just as B equal to mu H, J is equal to sigma E, Bx is del A del Y, By is del A del X. Similarly, Jx is del T del Y, del Y is minus del J del X. And psi is integration B dot ds. So similarly, I will be integration J dot ds. So basically what we are saying is that, why would we work with the electric vector potential? Now, suppose you have 2 points and you do not know anything else, but you know that the boundary condition that you know is the total current that is flowing through the surface. Let's say you have a surface and you know the total current that is flowing through the surface. In that case, you can, instead of using the conventional Poisson's equation, you can use this equation, which is in terms of the electric vector potential, and you can solve the equation just as you solve the magnetostatic equation. And you will solve for T, which is a vector. So it will have Tx, Ty, Tz. For a 2-dimensional, only Tz. Is this clear? We don't generally use this, but it is a possibility. You can use it. So for the sake of completeness, I wanted to mention this. Any questions? Okay, so Teja is here. Girish is not here. Okay. Any questions so far? So in the next lab, what you will do is you will learn how to model in COMSOL a permanent magnetic material. And in the next lab, you will learn how to work with the electromagnetic material. Before that, I will also cover something more. I will cover electromagnetism. And for the magnetostatic field, I want you to modify your existing program, which you have already submitted as an assignment. For your first assignment, I want you to modify that to work for to solve